Thank you very much for the invitation to give a talk today and for a nice introduction. Today, I want to tell you a little bit about my recent work on the Deift conjecture on the chord vector V equation. So I'll focus on the study of the chord vector V equation with bounded data and in particular almost periodic data. And this is joint work with Rowan Killip and Monica Vishan at UCLA. Okay, so first of all, let's just look at the chord vector V equation. So here's the equation that I'm interested in. On the left-hand side, I have one time derivative, three spatial derivatives. If we don't have this nonlinearity here on the right-hand side, this is the area equation, which is also going to play an important role in the talk later on. And the KdV equation is a nonlinear dispersive equation with this quadratic derivative nonlinearity. And in terms of domain, we're just thinking of our space variable x living on the real line. So this is an equation that was derived as a model for the propagation of long waves in shallow water and is a classical example of a dispersive equation. So in particular, waves with higher frequency travel at higher speed. If I look at wave-like solutions for my equation and I do not impose boundary conditions, in space, the waves tend to spread out, which we observe the phenomenon of dispersion. And another important characteristic of this equation is that it's completely integrable. So it has a lax pair associated with it. And in fact, the lax operator for this equation is the Schrödinger operator. So there's a strong relation between the study of the KdV problem and spectral properties of the Schrödinger operator. So the question that is going to drive the talk for a bit today is the following. So if I have some initial data that has some recurrence properties, do I expect those recurrence properties to extend to my solution at later times? And in particular, we're going to show that this is false if we start with initial data that is almost periodic and we evolve it through KdV. So that will be exactly what we're going to disprove regarding the Deift conjecture. Okay, but before we move on to that, let's just discuss some possible recurrence properties that would be of interest. So one classical type of recurrence would be the notion of periodicity. So considering data or functions that just keep on coming back to the same values with a fixed period. But we might have some form of recurrence that is not exactly periodicity, that our function doesn't return exactly to the same values, but close enough. And that is more or less the notion of almost periodicity. So I'll consider the definition of almost periodic functions as introduced by Bohr, which says that a function is almost periodic if it is continuous and it has dense almost periods. So for every epsilon, I can always find a length L epsilon such that every interval of length L epsilon includes an epsilon almost period. So a little L such that the difference between these two images of F is not exactly the same necessarily, but is really close. And there's an equivalent relation if that will help you think about it, which is due to Bochner. It says that a function is almost periodic if it is continuous. And when I look at any sequence and the corresponding sequence of translates from my function, this has a uniformly convergent subsequence. Okay. This might, if you have not encountered almost periodic functions before, that might seem a bit opaque, but a very classical example would be the sum of two continuous periodic functions, but with periods that don't match up. They're not commensurate. Or in particular, they're not rational multiples of each other. So individually, these two are periodic. When we put them together, it breaks periodicity. And another reason why we might be interested in talking about almost periodic functions is with this relation to the study of quantum mechanics and quasicrystals. So here just have a nice image of the structure of a quasicrystal. Okay. So back to our question. If I have initial data with certain recurrence properties, do I expect my solutions to KdV to to retain these recurrence properties. So this was proven to be true by McKean and Trubowitz if I start with periodic data. And then I know that my solution to KDV remains periodic in space and is almost periodic in time. And a natural extension of this was the conjecture posed by Deift that if instead I start with almost periodic data, my solutions and later times should be almost periodic in both time and space. And this conjecture has gathered a lot of attention from the spectral analysis community, but there hasn't been a definite answer provided to the question. So there's a lot of work being done, in particular on the study of the Schrodinger operator with almost periodic potentials, which is in close relation to the KdV equation with almost periodic data. And they've answered the Deift conjecture in the positive for particular subspaces of almost periodic data, such as, for example, when we have almost periodic data with exponentially decaying coefficients, so very smooth. And Demanik and his collaborators have also proposed a program that they believe will disprove the Deift conjecture. But what I observe in my collaborators is that what we should really focus on studying and exploiting is the dispersion of the equation. And in particular, we observed that the conjecture already fails for the area equation. So even without our nonlinear dynamics in the equation. And that's going to be the guiding force in the construction of our counterexample. Okay, so here's our first main result, which is that the Deift conjecture fails. In particular, we can construct almost periodic initial data and a solution that remains bounded for its time of existence, which is not almost periodic at a later time. And as I mentioned, our main ingredient here is really the dispersion. In particular, combining the failure of the Deift equation for the area equation, the Deift conjecture for the area equation, and a nonlinear smoothing effect. And the complete integrability that I mentioned before is also going to play a role, but only to establish a strong notion of uniqueness. And that is exactly our second result, that we can prove uniqueness of solutions to KdV that are merely bounded without further assumptions on its spatial asymptotics or regularity. So if we have two solutions that are bounded both in time and space, if they agree at 0 or even agree at a different time, then the two solutions are almost everywhere equal to each other. And you can think of this result as a form of unconditional uniqueness, where that applies to bounded initial data. And of course, enveloped in these bounded initial data and bounded solutions, we will include periodic solutions, almost periodic solutions, and a variety of other interesting spatial asymptotics as long as our solutions remain bounded. All right, so what I want to tell you in more detail now is a bit more about how we establish uniqueness, and then we'll go back to how we disprove the Deift conjecture. All right, so the idea for our uniqueness argument is really to pursue a Gronal argument. But we need to find a suitable choice for our distance function to measure how far our two solutions are from each other. So just as a guiding principle, let's just look, for instance, at the difference of our two solutions, square it, and see what happens if we take a time derivative. So if I do that and I plug in my equation and I do some rewriting, I obtain the following. But I'll have too many derivatives falling on my terms. This is going to require too much regularity. Let's instead try and test our function against a psi, which is, let's say, Schwanz, something smooth and nice. So if I do this, I then can do some integration by parts to peel off some derivatives from my functions, and I arrive at something from this right-hand side. And an easy choice of psi would be, well, in this case, just smooth, if I pick it equal to 1. just the constant function one. In that case, all of the terms that have derivatives would disappear, not just be left with this term. And I can just get rid of these derivative terms and place them in L infinity. And from this inequality, I'd be able to write apply my Grundle estimate to get an estimate on this result here, based just on these norms here. The problem is that that would still require too much regularity from my solutions. I'd still have to be L2, I'd still need this first derivative and the boundness of this first derivative. I could play around with this choice of psi to try and get something better, but I still have these terms in red here that it's not exactly clear if I could at least get rid of all of these derivatives eventually just by choosing psi nicely. So this seems to suggest that looking at this sort of distance function is not a good idea. Maybe what we should do altogether is try and find a suitable change of variables. Instead of working directly with Q, work with some different function that is related to it. And in that choice, we're going to be guided by the complete integrability. So KdV is completely integrable, which means that it has a lax pair associated with it. So two operators, L and P, and having Q that solves the KdV equation is the same as imposing this on these operators. And our lax operator is exactly a Schrodinger operator where Q is its potential. And P is not too important for us, so I'll omit it. So what this equivalence tells us is more or less that the spectral properties of our lax operator are conserved under the KdV flow. So what we really want to use from the complete integrability is the diagonal Green's function that comes associated with this L plus kappa square operator. And this diagonal Green's function is going to be our change of variables. This is a change of variables that has been instrumental in proving very strong optimal results in well-posedness of dispersive equations, which are completely integrable, such as in the work of Kilip and Rushan with the method of commuting flows. Here we use it for uniqueness. So this diagonal Green's function can be made sense of with respect to this series here. And the important thing for us, which also requires a bit of work, is that we can make sense of this object by just having Q being a function in L infinity without further regularity. And not only can we make sense of it, we can make sense of its first and its second derivative, and they're bounded without imposing further restrictions on Q. Okay. And something else that I want to mention is that we can make this second term here relatively small compared to the first one. So you can think of G as being more or less like 1/2 kappa. So something that is positive because our kappa is a positive constant. So something far away from 0, because in the next slide, you're going to see something that where I'm dividing by 0 and I'm dividing by G. Okay, so I can also write dynamics for this diagonal Green's function. And to convince you that you can really think of this as a change of variables, I can write an equation that allows me to recover Q if I know G, G prime and G double prime. So our proof really focuses first on showing uniqueness for our G's and then transferring it to the Q's through this equation here. Okay, and the main difficulty is in showing uniqueness for the G's, in particular in choosing the correct distance function to prove this, which in our case is going to be this. So G1 minus G2 squared over 2 G1 times G2. Okay, so with this choice of distance function, if I take a time derivative as before, I can rewrite what I get on my right-hand side to make appear a lot of terms that depend on this quantity. And these A2, A1, and A0 are harmless. They just depend on quantities that we can control its L infinity norm so suitable for our orthogonal argument. But even with this nice choice of function where a lot of these terms appear again, I still have a term that doesn't quite look like what I needed to look for my orthogonal argument. So to handle this problematic term, again, B only has nice things that I can just put in L infinity. What we're going to do is the same thing as before. We're going to test against a nice function, which we've chosen as this sesh here. And we're going to use integration by parts to put the derivative on this term. And then the only thing that we're really missing to see our U term is a square. So we just use Cauchy inequality on this product of G1 minus G2 and B. We get a square here and a square there, but this term is never going to look like our U term. So we want an epsilon there to guarantee some smallness eventually, something to be chosen later, and we pay the price of 1 over epsilon on the other term. So from this derivative here, we get a 1 over r, which we want because we want eventually to take r to infinity, and we want to have some decay of these terms. And everything that is on this side is just nice and bounded. So we get something bounded and our small quantity epsilon. So then the idea is that we have to pick this epsilon small enough that we can guarantee that this second term is decaying as r goes to infinity, but without ruining the decay of the first one. So this choice of r to the power of -1/2 works. So combining this estimate of the bad term with how we handle the first one, we get something on which we can apply our orthogonal estimate and this sort of exponential result here that still has decay as r goes to infinity. So from this, we can actually prove that this for every r positive is equal to 0, from which we conclude that G1 is equal to G2 almost everywhere. Okay, and now we need to translate this onto 2r Qs. And we use exactly that equation that allows us to recover Q from our Gs. In fact, if I just look at the difference of Q1 minus Q2, I can always rewrite this difference using this equation here into terms that always see a factor of G1 minus G2, from which I conclude that Q1 must be equal to Q2 almost everywhere because of the uniqueness of the Gs. Okay, so the main difficulty here is first finding this distance here. This part of just figuring out what to do with all of these terms is fine as long as we have functions which are smooth. And then the second difficulty really comes from justifying that all of this still makes sense when Q is only in L infinity. And that's what requires a lot of the work in the paper in terms of the uniqueness. In particular, we need to think about smooth approximating sequences for Q by taking modifications and also guaranteeing that it has sufficient decay. Okay, so this is our uniqueness result. So back to our main focus, which is the Deift conjecture. So what we want to do is we want to start with functions that are almost periodic. We want to evolve that data through KDV, and we want it to eventually not be almost periodic. So the question is, how are we going to break almost periodicity? So if I have two periodic contiguous functions and I add them together, and they have periods that are no rational multiples of each other, I'm almost periodic. So one way of breaking almost periodicity is if I still take the sum of two periodic functions with periods that are not rational multiples of each other, but I remove the continuity assumption. So instead of using a cosine, for example, I can think of a square wave. So a wave of this form, which is periodic, definitely not continuous. So the fact that both of them are not continuous is going to lead me to the lack of continuity. And the fact that they are periodic, but their periods don't match, is going to break the fact that they have dense almost periods. So if I look at a sum of two square waves, this is not almost periodic, but it's still bounded. And it is this sum of two square waves that is going to be our basis for our counterexample. Okay, so, oh, sorry, I clicked too much. Okay, so the guiding observation to go in this work is really the fact that the Deift conjecture fails for the area equation. And this is somewhat related to the Talbot effect. So in 1836, Talbot performed an optical experiment where he observed light passing through a diffraction grating. And he noticed that there was a sharp pattern that repeated at certain multiples of a distance, which is known as the Talbot distance. And this has further been studied further by a variety of authors, both from a rigorous perspective and also through numerical experiments. And we can think of it, well, today we think of it more of a notion of the profile of solutions to dispersive equations arising from periodic data depends strongly on the algebraic properties of time. And I want to emphasize what was actually done by Oskolkov, who studied exactly the profile of solutions to linear dispersive equations, a variety of those with periodic initial data, which is also a bounded variation. And it keeps on moving 2 slides, sorry about that. So what did he actually prove in the context of the area equation? So the linear part of KdV. So what Oskolkov proved is that if I start with data f, which is periodic, with a fixed period alpha, and is also bounded variation, then the solution to the area equation, which I'm going to represent like this, satisfies the following 2 things. So first of all, is bounded for all times and in space as well. And at irrational multiples of the period, it is continuous. And it also has a very different behavior at rational multiples of the period. But continuity at irrational multiples is going to be what's important for us. In particular, if I start with data that is periodic and a band of variation, but it's not continuous, and I evolve it through the area equation up to a time which is an irrational multiple of the period, then I gain continuity. So I managed to start from something that is not continuous and arrive at something that is continuous. And I can then use time reversibility, take this continuous data as my initial data and evolve it backwards to arrive at something that is discontinuous. So why do we care about this? Exactly because of our square waves. Our square waves are of bounded variation and they're discontinuous. So Oskolkov's result says that if I evolve it to a time t0, which is an irrational multiple of both the periods of these 2 functions, then I get to something that is continuous. And because of the structure of this equation is therefore almost periodic. So this here, which is now an almost periodic function, would become our initial data that then we can evolve backwards in time to the area equation and come back to our square waves, which are now not almost periodic. So this here is exactly our initial data to disprove the Deift conjecture for the area equation. And now we want to extend this to KdV. Okay. So again, because of the time reversibility of KdV, we can do a similar idea of we just need to start with our square waves and we need to find a solution at a later time is almost periodic. And due to time reversibility, we can take that later time solution as our initial data, evolve it backwards to something that is not almost periodic. And this here would be our initial data for a counterexample. So what we're going to focus on is the equivalent problem of starting with our square waves and proving that we can construct a solution that becomes almost periodic at a later time. Okay, so the first question is, can we even construct solutions for this data here? For area, we knew that we can just evolve those two periodic data separately and glue them together, and we get a solution for the area equation with this initial data. But this is, of course, not true for KDV because it's nonlinear. So that's our first issue, which is how do we construct data for this? And then what do we want to do? And the reason why we're picking these square waves is because we have information about the linear solution. In particular, we already know that at irrational multiples of the two periods, that this here becomes almost periodic. So if we can construct solutions, the focus should be on proving that the nonlinear part also has some good behavior. It's also almost periodic at a later time. Okay, so here's a bit of a schematic of what we're going to do. So here is just the scheme that we discussed before of I start with my square waves. My first question is, can I actually evolve it to get a solution at a later time? And if that exists, I want to use what I know by Oskolkov, that my linear solution is already continuous and almost periodic at a later time. And then we want to prove that our nonlinear part also becomes continuous and has the right structure to be almost periodic. And that's going to be our nonlinear smoothing effect. And then we take that as our initial data, which is almost periodic, and evolve it backwards, just through time reversibility. And at that point, we also need to use our uniqueness of bounded solutions to guarantee that that is really the only possible evolution through KDV with that initial data. Okay, so first of all, let's just discuss the local well-posedness, and then I'll tell you a little bit more about the nonlinear smoothing. So the local well-posedness was actually already available to us due to the work of Tsugawa. So if I look at my data, this sum of two square waves, I can write a Fourier series representation for each of them. I can put them together into just one sum that is now indexed by a vector in Z2. And I can think of this combined coefficient here as the Fourier coefficient for my sum of the two square waves. And here, don't need to worry about the fact that we're dividing by alpha dot k, because our choice of this one and alpha is that they're not rational multiples of each other, or they're rationally independent. So if I take any vector that is in this Z2 excluding the origin, I know that alpha dot k is going to be non-zero. Later on, to make our life easier, we're also going to impose a more quantitative version of this assumption. Not only will we want this to be non-zero, we want it to not be too close to zero. Okay, so the spaces that Tsugawa introduced in his work to study sort of quasi-periodic data, but that might not have continuity, were these spaces G theta, where he imposes that the data needs to be written in this sort of Fourier series format, and it has a bounded norm G theta, where you can think of this norm as being a Sobolev, L2-based Sobolev norm adapted to this quasi-periodic setting. So we have my Fourier coefficients. I'm adding theta derivatives to each of my entries, and I have this funny looking term downstairs. What this alpha dot k is doing is really trying to handle the fact that although I'm imposing the alpha dot k is different from zero, it might actually be really, really close to zero for certain choices of k. So this here is trying to balance that effect. Okay, and we're taking everything in an L2 sense. So our data, our sum of the two square waves, actually belongs to this space G theta because it has this Fourier series expansion, and this norm is finite as long as I impose that theta is less than 1. So as long as we can guarantee that we can apply Tsugawa theta less than 1, we're fine. And that is the case, because Tsugawa tells us that KDV is locally opposed in G theta as long as theta is greater than a quarter. And the solutions exist. They are continuous in time with values in g theta. And we also need to intersect with these XSB-like spaces adapted to the quasi-periodic setting. And the fact that we have this extra structure for the solution that Tsugawa constructs is going to be important for our nonlinear smoothing effect later. So what Tsugawa does is he applies the Fourier restriction or method of Bourgon, but with these different XSB spaces adapted to the quasi-periodic setting. And what these spaces do, these X spaces, is you can think of them as space-time Sobolev norms that are well adapted to the dispersive nature of the equation. In fact, if I take a space-time Fourier transform of my function, or if I take a space-time Fourier transform of my linear solution for Airy, it's going to be supported on tau equals to alpha dot k cubed. So what this weight here is doing is penalizing functions that are far away from the support of the space-time Fourier transform of my linear solution. Okay, so just because this is going to show up later, we have this weight and time, and in space we're measuring our functions in this g theta space. So we have our derivatives above and our weight downstairs. All right. So now we have solutions.
Andrea, I have a question.
Yes.
So this is Hiro. Your function initially the sum of two, square functions. Mm-hmm. They don't belong to this analytic class of initial data where the global well-posedness was proven by Damanik and the Goldstein.
No, they're not regular enough.
Right. Okay. Because they only have this kind of analytic exponential decay Fourier coefficients, right? Global well-posedness for the quasi-periodic initial data.
Yeah.
All right.
So our Fourier coefficients don't decay fast enough.
Okay.
For that to apply. Yeah. Okay. So on to our nonlinear smoothing. So this, what we're going to prove is that if we impose a Diophantine condition, so this quantitative version of the alpha dot k being different from 0, we're actually imposing that it's not too small, then we can, if we take our solutions from Tsugawa and we impose some restriction or regularity, which again, the important thing is that it's still less than 1, so it still applies for our sum of square waves. If I look at the spatial Fourier coefficients of my solution minus my linear part, so if I just look at the nonlinear contribution of my solution, these are absolutely summable, which in turn tells me that my nonlinear part becomes continuous for every time. And because of the structure of our solutions that we know that have this Fourier series expansion, it means that they're also almost periodic. Okay, so the important thing of this nonlinear smoothing result is that for the linear solution, we knew that there were particular times, these t naughts, which are irrational multiples of the two periods of the square waves, that this linear solution is almost periodic at specific times like those. This nonlinear smoothing says, if I remove that, my nonlinear part is actually almost periodic for every time that the solution exists. So the failure of the Deift conjecture is really a linear phenomenon, is driven by the linear solution, not the nonlinearity. Okay. And you can think of this result as being akin to the nonlinear Talbot effect that was proven by Erdogan and Siracusa in the periodic setting. And we believe that this is a first instance of a nonlinear smoothing as a result in the almost periodic setting. So how do we prove it? So I'll give you some brief ideas of how we go about this result. So we want to show something on our Fourier coefficients for a nonlinear part. So let's just write those down. And these term here on the right hand side is what we need to prove is absolutely summable for everything. And as usual with KDV, the main difficulty is really going to come from this weight here, this alpha dot k just the derivative in the nonlinearity. So to simplify our life a little bit, let's just think about a bit of symmetry and reducing our problem. So I'm going to assume that alpha dot m is greater than alpha dot n, where m and n are the frequencies associated with the first and the second factors here. And then I can just think that the first entry of this vector m is greater or equal than the second one. And this is going to help me control the derivative in my nonlinearity. So I can write this alpha dot k as alpha dot m plus alpha dot n, because k is equal to m plus n. I'm just bounding it by the largest of the two, which is alpha dot m. And then this here is really just m1 plus alpha m2, and I can bound it by the largest of those, which is just m1. Okay, so this tells me that I can control the derivative of my nonlinearity if I place it all in my first entry. But that's probably going to require too much regularity on our functions, which we do not want, so you have to use something else. So first case, and with a lot of these arguments, there's a lot of cases, but we'll just focus on some of them. If m1 is not the largest frequency, so if I can at least bound it by one of the other three frequencies involved, then I can split this derivative between m1 and one of these other frequencies. But at this point, it's also useful to use the fact that our functions live in these XSB spaces. So they are not only in L infinity in this G theta, they also have some form of time regularity in these weighted spaces. So one of the ideas in using these XSB spaces is we can use these weights, these tau minus alpha dot cube weights, to trade time derivatives by spatial derivatives. So if I look at the two weights that show up associated with the space-time Fourier transform of my two factors in the nonlinearity, that is bounded from below by this sum here, and using this famous, maybe I'll write it, this famous relation of KdV, I can write it this way, which in my format with alpha dot k gives me 3 alpha dot k, alpha dot m, and alpha dot n. So with this, the way that we should be reading is I can use a half power of my time weights in the XSB norms to gain a negative power of these. So I gain alpha dot k to the power of a half, alpha m to the power of a half, and alpha dot n to the power of a half. And the first one is exactly going to kill a half of my derivative in the nonlinearity, and the other ones are going to be useful because if you recall, in my G theta spaces, I need these negative weights downstairs to the power of a half. Okay, so doing exactly that, I get my weights here, I gain my alpha powers downstairs, and I kill a half of my derivative from the nonlinearity. Now, I know that I can bound alpha dot k by m1, so I can control this here by m1 to the power of a half. And then I've also placed all of these derivatives onto my functions, which now appear down here. There's nothing else that I can do with these. I'm just going to use Cauchy-Schwarz, be done with my functions. They live in the space they're allowed to live in. And now the focus moves to guaranteeing that these sums here are finite. Okay. And I'm left with this power of m1 that I need to use something that is downstairs to kill it. But I know that m1 can be controlled by one of the two other frequencies. So let's assume that m1 is less or equal than m2, which means that I can split this power here between m1 and m2. And now to handle my four sums, I need 2 theta to be greater than 1 and 2 theta minus half to be greater than 1 as well, which imposes that theta is greater than 3/4, which we're happy about because, again, we only care about having theta less than 1. Okay, so what about the other case? What if M1 is much larger than all the other frequencies? Well, when handling the functions, we can do exactly the same thing. The problem arises when we want to split this power of M1 above. Because now, nothing of what's downstairs apart from this first factor helps us. So all of our loss really has to go into this first term here. So now we are forced to impose that 2 theta minus 1 is greater than 1, which pushes our regularity above 1, which is not what we want at all. So in this situation, we need something else. What we're going to use is the normal form approach, or the idea of integrating by parts. Okay, so in this regime, we can get some extra information on our frequencies. In particular, can conclude that the first entry of the generating frequencies, the Ks, is comparable to the first entry of the Ms, which are much larger than all of the other frequencies. And also this alpha dot terms, the one that appears in the nonlinearity is comparable to the one associated with our first factor and much larger than the one associated with the second factor. Okay, and you'll see later why this is important. Okay, so I want to use this idea of integrating by parts, but first I'm going to rewrite my nonlinearity, or the term that I care about, by using the interaction representation. And notice that if I prove that this quantity here are absolutely summable, then the same thing follows for the U's. Okay, so what do I gain by writing this interaction representation? Is exactly this exponential here. The now depends on these alpha k, alpha m, and alpha n, which we had to work so hard before by using the XSP spaces to gain. What we do now instead is rewriting this exponential as a time derivative, which pushes all of these exponents downstairs. And if we can get rid of our time derivative, in fact, this alpha dot k will kill immediately this one in the derivative. And we get some alpha dot m and alpha dot n for free. So what we do is we just do integration by parts. We get two boundary pieces. We get an n1 and an n2. Our boundary pieces look like this, where we've already killed our alpha dot k. And n1 arises when the time derivative falls on the first term, the m. So you see that we have m generating new frequencies from when we plug in the equation for dTVm. And we're only left with alpha dot n, because when we plug in the equation again, we add an extra derivative. In particular, we add alpha dot m, which is why this term doesn't appear here. And an analogous thing for the second term, which corresponds to when this time derivative falls on this Vn term, and we plug the equation again. All right, so our boundary pieces are going to be mostly okay. We can use the information that we have on the frequencies, and we can manage to sum this. The most problematic term is going to be this n1 term, exactly because this alpha dot n here that possibly could help us can actually be really small. So if you recall, we know that alpha dot n can't be 0, but it can be really, really small. And it is to control how much we're losing from this when it's really, really small, that we have to impose this Diophantine condition to say that it can't be that small. Okay, so the boundary pieces are mostly okay. N1 is the term that really is going to need some extra work. In fact, we need to undo what we've done with the interaction representation to get here, write this in terms of U again, so that we can use the fact that our U term is in the XSP spaces. In fact, we want to use that idea again of trading time derivative by spatial derivative. Okay, so again, we have some subcases. one of them being that this quantity is actually not too small, that we can trade this alpha.n by these other alpha.j and alpha.l terms. They can just become associated with these two terms when trying to place them in this G theta spaces. But the terrible, horrible cases when indeed this alpha.n quantity is really, really small and smaller than everything else that we're handling. And in that case, we need our Diophantine condition to guarantee that it is not that small, that even the loss that we get there, we can translate it to a loss in the spatial derivatives. And we're going to use, again, the idea of trading time derivatives by spatial derivatives. So in this case, if we look at the time weights that are associated with these functions, we can write them in the following way, and we get this sum here. And now what we have to use is the relation that is normally associated with the modified KV nonlinearity, which is that if I have a cube of the sum and these differences, I can write this as 3 times the product of the sums individually, which is exactly what I've written here with this correspondence with the alpha dots. And it's not exactly clear immediately if this is a good thing, but it is, because this first term looks like an alpha.j, the second one looks like an alpha.l, and this last term, because m is the frequency that generates these j and l, this looks kind of like alpha.m, which is just like m1, which is a large frequency. So it's going to help us with the summations. So this says that if I can use half derivative of these time weights, I gain the half of these factors that I want downstairs to place these terms in G theta, and I still get some help to try and do my sums. And to handle some of the loss here, we really need to use our Diophantine condition to guarantee that it's not too small. Okay, so those are the main ideas for our nonlinear smoothing effect. It's really exploiting the fact that we know that the functions are not only in the CT and these G theta spaces, but also that they have this additional structure of being in these XSB spaces, and exploiting the dispersion through these XSB spaces, and also this normal form approach. Okay, so just a recap of how we construct our counterexample. So we start with our sum of the 2 square waves. We use the result of Tsugawa to construct a local and time solution that has this Fourier representation and lives in these G theta and XSB spaces. By the Talbot effect, the result of Oskolkov, we know that at times T naught, which are irrational multiples of the periods of our square waves, this linear part becomes almost periodic. And through our nonlinear effect, we know that the nonlinear part is also almost periodic. This time, it's actually almost periodic at every time that the solution exists. So now we take this UT nod at this special time as our initial data, which is almost periodic. And using time reversibility, we know that we can evolve through KdV backwards in time to come back to our square waves, which are not almost periodic. And indeed, this is the only possible evolution arising from KdV from this initial data, because our solutions are also bounded. So our uniqueness for bounded solutions applies, and this effectively disproves the Deift conjecture. So the idea that if I start with almost periodic data, the solutions to KdV should remain almost periodic in time and space, which we've effectively proven is not the case. So that is what I wanted to tell you today, and thank you very much for your attention, and I'm more than happy to answer any of your questions.